Today, we're going to look at another class of functions. At this point, we've looked at linear functions, we've looked at polynomials, we've looked at rational functions. Now we want to kind of finish off this semester with a different class of functions called exponential functions. And essentially, there's a standard form for an exponential function. There's different ways to write it, but generally speaking, something like y equals a times b to the x. We will use that when we get to problem solving with applications of it. I'm sure a lot of you have probably seen that before. For right now, before we get there, we're going to make it even more basic. We're just going to let a be 1, and we're going to let y equal b to the x. That's exponential because my variable, my x, is actually a power. It's not the base right here. It looks similar to a polynomial, y equals x squared. But in this case, for the polynomial, the x is a variable, the base is a variable, and the power is constant. It's always squared. Here, the x, the thing that changes, is your power. Your base is constant. Something like maybe 2 to the x. Here, the 2, the base stays constant, and you change the power. So just kind of keep those straight in your head. With exponentials, the power changes, not the base. Throughout the semester, anytime we had a new function, we generally graphed it first so we could get an idea of what was going on. So we're going to do that here. So say we take a basic exponential. We'll just use y equals 2 to the x. And we'll plot some points and see what's going on. So let's see. If x is 0, you get 2 to the 0. Anything raised to the 0 is 1. So we get 0, 1. If x is 1, y is equal to 2 to the 1, which is 2. If x is 2, y is 2 squared, which is 4. If x is 3, y is 2 cubed, which is 8. We're going to do more points, but at least to start, we can start plotting some points. We get the point 0, 1, then the point 1, 2, then 2, 4, then 3, 8. And we can kind of see this just gets really big really fast. That's where the expression grows exponentially comes from. It gets big really fast. But we want to know what happens over there on the left. So look at some negative values. If x is negative 1, you get 2 to the negative 1. I'm assuming we're all aware of how exponential powers work and all of that. If not, we can go over it in a few minutes. But if you have a negative exponent, 2 to the negative 1, that just means reciprocal. So that's 1 over 2 to the 1, which is 1/2. If you plug in negative 2, that's 2 to the negative 2, which is 1 over 2 squared. Negative powers are reciprocals, which is 1/4. And it should be obvious if you plug in negative 3, you get 2 to the negative 3, which is 1 over 2 cubed, which is 8, 1 over 8. So clearly, on this side, at negative 1, I get 1/2. At negative 2, I get 1/4. We just said at negative 3, I'd get 1/8. And this will get smaller and smaller and smaller. It will never actually hit 0 because all of these negative x's give me reciprocals. The numerator is always 1, which means the fraction is never 0 because it's only 0 if the numerator is 0, which means this does get smaller and smaller, but it never actually hits 0. It just has a horizontal asymptote as it approaches 0. As far as it goes, that's pretty much it. For these exponentials, they all have this form with one exception that we'll go over in a second. If you had y equals 3 to the x, well, at 0, you get 3 to the 0, which is 1. It would still go through this point. As x got bigger, 3 to the 1, 3 squared, 3 cubed, y would get bigger, and it would look the same. On this side, as x gets negative, negative 1, negative 2, negative 3, this gets smaller, 1/3, 1/9, 1/27. They look the exact same. So as far as exponentials, they have a horizontal asymptote at 0, and unless you're moving them around, they all go through the point 0, 1. Because when you plug in 0, you get anything to the 0 is 1. There is one exception to this, or one class of exceptions to this. Suppose our function was y equals 1/2 to the x. Well now, if we plot some points, we'll only do a few of these. If you plug in 0, you get 1/2 to the 0, which is still 1, so it still goes through there. If you plug in 1, you get 1/2 to the 1, which is 1/2. If you plug in 2, you get 1/2 squared, which is 1/4. And now clearly, you go through 0, 1, then 1, 1/2, 2, 1/4, and now it's getting smaller. Using intuition on this side, then, it should get bigger. If you plug in -1, you get 1/2 to the -1. Negative powers are reciprocal, so it flips that, and it becomes 2 to the 1, which is 2. If you plug in -2, you get 1/2 to the -2. Negative powers are reciprocals, so it becomes 2 squared, which is 4. And it's clearly getting bigger, so this works. So basically, as far as it goes, all your exponential graphs either look like this or like that. They all go through 0, 1. Again, unless we start manipulating them and moving them around. And the only thing you need to tell if it's going to go increasing or decreasing is to look at the base. If the base is greater than 1, 2, or 3 that we had, it'll go up and look like this. If the base is between 0 and 1, it'll go downwards. Most of the problems we look at will have exponential growth where the base is greater than 1, so we'll use this one a lot. But be aware it can decrease if your base is between 0 and 1. Okay, now we want to kind of mess around with these things a little bit. First off, really quickly, once we know the graph, we can do what we did before and translate our graphs. So suppose I wanted to graph y equals 2 to the x plus 1 plus 3. Well, we understand that's just y equals 2 to the x translated. So, graph all your translations. Y equals 2 to the x, standard exponential graph like that. But we don't have 2 to the x, we have y equals 2 to the x plus 1. If we remember our transformations, when you add inside the function, inside the exponential, that's a horizontal shift, plus 1 will shift me 1 to the left. So in this case, use the point 0, 1. That's going to go 1 to the left, so it'll be the point -1, 1. And then the graph stays the same. But we don't actually have this. We have y equals 2 to the x plus 1 plus 3. Again, if we remember our transformations, if you add outside the function, that shifts vertically. Easiest way to see this if you're shifting vertically, move your asymptote. Horizontal asymptote here is at 0. If we shift it up 3, it goes up to 3. This point at -1, 1 goes up 3. So it's -1, 4, right above the asymptote where it should be. Now, just sketch your regular exponential and you're done. So the thing to be aware of, this is no different than all the transformations we did before. Once you know a basic graph, in this case the exponential graph, you can do all the transformations that you're used to doing. A couple of more things we want to cover. As far as it goes, when you start talking about exponentials, some of them you see quite a lot. Some bases you see a lot. Y equals 2 to the x. When the base is 2, everything doubles. We graphed it, we plotted some points, we see that. That occurs a lot. Things double a lot in the real world, and it's very common in problems. So you'll see that one a lot. There's another common exponential. Y equals e to the x. If you've never seen e to the x before, it's on your calculator. We're going to use it a lot. So make sure to check your calculator and try to find the button because we'll use it. But ultimately, it doesn't really matter. Don't get too confused. Essentially, if you plug it into your calculator, if you plug in e to the 1, you get 2.71, and then it keeps on going. So basically, this number e is just the number 2.71, which means y equals e to the x is an exponential with a base that's 2.71, which means if nothing else, the base is greater than 1. So if you wanted to graph e to the x, it'll look the same as a regular exponential. And it goes through 0 and 1, just like normal. So it looks a little bit different, but don't be confused by it. We're going to spend a lot of time with the exponential function and this e to the x, so we'll get used to it as we work. It actually is really important mathematically. We see it a lot in calculus. It is the function that is its own derivative. If you don't know what that means, don't worry about it. You'll see it in calculus. The last thing I wanted to mention is there are a few properties of exponentials that we're going to use to solve problems eventually, so we might as well cover them now, at least one of them. And there's a rule that says if a to the x equals a to the y, then x equals y. So if you have 2 to the x equals 2 to the 4, then you have two exponentials that are equal with the same base, then x has to equal 4, which is obvious from there. The way we actually use this in problem solving is, if we have 2 to the x equals 4 to the x plus 1, well, that's two exponentials that are equal. We know by the property, if you can write them in the same base, then we can drop the bases. In this case, 4 is 2 squared, so we can rewrite this as 2 to the x equals 2 squared to the x plus 1. Now apply your rules of exponents. If you raise an exponential to a power, those get multiplied. So you get 2 to the x equals 2 to the 2x plus 2. But now we have two exponentials that are equal with the same base, so we can just drop the bases. And we end up with x equals 2x plus 2. Now just do some algebra, subtract the x over and you get x, subtract the 2 over, you get negative 2, and you're done. That's pretty much all we need to go over today and all you should need for your homework. Essentially though, this is going to become really, really important. When we start solving more advanced problems, we're going to be using these properties over and over. So you just want to get this idea in your head. If you have two exponentials that are equal with the same base, you can drop the bases and solve for the powers, like we did right here. One last little thing to be aware of. If you have something like 3 to the x equals 7 to the x plus 1, you have two exponentials that are equal, but the bases are not equal. And in this case, there is no way to write 7 as a power of 3. So this trick would not work. You'd have to use other tricks. We don't have those tricks yet. We'll see them later in this chapter. But for right now, essentially, we just wouldn't bother with that. We'll do other tricks later. Right now, we're only going to concern ourselves with ones where we can write them in the same base. That's it for this lesson. If you have any questions, feel free to email me as you're going through your homework, and I'll kind of expand on this some more if you have any other questions.